To lecture 9 on circles. In the previous lecture, we had discussed about we had solved some problems related to common tangents of two given circles. So, in this lecture, we will talk about the angle of intersection between any two given circles, and then we will move to finding the condition under which any two given circles are orthogonal to each other. We will also define something that is known as the radical axis between any two given circles. So, let us start with defining the angle of intersection of two given circles. So, suppose the equation of two circles is given to us, and let us say that the two circles are intersecting each other. So, obviously, the angle of intersection is already defined for two circles which intersect each other. If the two circles are not intersecting with each other, then the angle of intersection is not defined in that case. So, let us say that these are the two circles which intersect with each other. So, this is the first circle S1, this is the second circle S2. So, let us say that the centers of these two circles are at O1 and O2. The equation of the first circle is, let us say, x square plus y square plus 2g1x plus 2f1y plus c1 equals 0. So, this is S1, and the equation of the second circle S2 is x square plus y square plus 2g2x plus 2f2y plus c2 equals 0. So, these two circles intersect at these 2 points. Now, let us draw a tangent to the first circle. So, a tangent at this point of intersection. So, the tangent will look something like this. So, essentially this is going to be 90 degrees. Similarly, let us also draw a tangent to the second circle at the same point of intersection. So, that tangent is drawn in red here. So, that might look something like this. So, this is the straight line tangent to the second circle at this common point of intersection. I will call it T2, and the tangent to the first circle at the same point of intersection I will call it by T1, and then let this angle between these two tangents be theta. So, this angle between the two tangents to the two circles at this point of intersection. So, this angle is what is known as the angle of intersection between the two circles. So, now given the equation of the two circles, we should be able to find this angle of intersection theta. So, for that, let us denote this point of intersection by A, and let us also connect O1 O2 by a straight line. So, now what we have is a triangle O1A O2. So, this is a triangle that we have. So, the length of the side O1A is equal to R1, which is the radius of the first circle S1. Well, R1 of course is equal to the square root of g1 square plus f1 square minus c1, where we already know the values of g1, f1 and c1 because the equation of the first circle is given to us. Similarly, we can find this length O2A, which is actually the radius of the second circle, and that can again be found from the, since we already know the equation of the second circle, we can we know the values of G2, F2 and C2. So, R2 will simply be square root of G2 square plus F2 square minus C2. And then of course, since we already know the coordinates of the center. So, the coordinate of the first center, the center of the first circle is minus G1 comma minus F1, and then the coordinates of this point O2, which is the center of the second circle, is minus G2 comma minus F2, and then the distance between them, which is so O1 O2, the distance between the two centers is given by square root of G1 minus G2 whole square plus F1 minus F2 whole square. So, now what we have here is we have a triangle O1AO2, and we exactly know the lengths of its three sides, and therefore, now it should be possible to also find the three angles of this triangle. But then we are actually asked to find this angle theta. What we also realize is that since T2 is a tangent to the second circle, this angle is also 90 degrees. So, now if we look at this point O, so we first have this angle which is 90, then we have theta, and then we have this angle which is 90, right, and then finally we have this angle O1A O2. Since the sum of all these angles should be 360, what we have is that, so the first angle is 90 degree because of this. So, that is the angle between this O1A and this tangent T1, that is 90 degrees. So, pi by 2 plus, and then we have the angle of intersection of the two circles, which is this angle theta, plus then again we have 90 degrees between this the normal O2A. So, the angle between O2A and T2 is 90 degrees. So, we have again pi by 2, and then plus angle O2AO1. So, angle O2AO1. So, sum of all this should be equal to 360 degrees, which is 2 pi, and therefore, from there we can say that angle O2AO1 must be equal to pi minus theta. We will write here pi minus theta. Now, we will simply apply the cosine law to this angle O2AO1 of this triangle. So, by the cosine law, cosine of this angle O2AO1 is equal to the sum of the squares of the two sides, which which are adjacent to this angle, or so the two sides are basically in this case R2 square and R1 square. So, R1 square plus R2 square minus the square of the side which is opposite to this angle, which is, so it will be minus of this the distance between the two centers, the square of that, divided by 2 times the product of the length of the sides adjacent to this angle. So, divided by 2 times R1 R2. So, of course, now from here taking it further, now we already have expressions for R1 R2 and O1 O2 in terms of the because we already know the value of the G1 G2 and F1 F2 and C1 C2, since the equation of the two circles is given to us. So, we should be able to exactly find out the cosine of this angle, but we already know that since angle O2A01 is pi minus theta, cosine of angle O2A01 is cosine of pi minus theta, which is equal to minus cos theta. But we also know that this is equal to, from the previous slide, we will just replace the expressions for R1, R2 and O1, O2. So, these three expressions will be substituted here, and thereby we are going to get this cosine minus of cosine theta, which is cosine of angle O2A01, to be equal to, so R1 square will be G1 square plus F1 square minus C1 plus R2 square will be G2 square plus F2 square minus C2 minus of O1 O2 whole square. So, O1 O2 whole square will be G1 square plus G2 square minus 2 G1 G2, then plus F1 square plus F2 square minus 2 F1 F2. So, this is the numerator, and the denominator we have 2 times R1 R2. So, it will be 2 times square root of G1 square plus F1 square minus C1 times square root of G2 square plus F2 square minus C2. And this, so essentially what we have is that cos, so this is minus of cos theta, therefore cos theta, where theta is the angle of intersection between the two circles. So, cos theta will be equal to C1 plus C2 minus 2 times G1 G2 minus 2 times F1 F2 divided by 2 times square root of G1 square plus F1 square minus C1 times square root of G2 square plus F2 square minus C2. And we already know that since since pi minus theta is between 0 and pi, so it is clear that theta also is going to be so theta is going to lie in the range, 0 to pi, and therefore the value of theta will be nothing but, so theta will be nothing but cos inverse of this right hand side. So, theta will be equal to cos inverse of, so the argument of cos inverse will be this expression. Now, let us see the condition under which two circles will be orthogonal. So, when we say two circles are orthogonal, so two circles are said to be orthogonal if and only if the angle of intersection between them is pi by 2 or 90 degrees. So, now let us see what is the condition under which, or which the condition that must be satisfied in order that two given circles are orthogonal to each other. And that should not be very difficult from here, because if two circles are orthogonal, then this theta must be equal to pi by 2. But since cos of pi by 2 is 0, it is clear that for two circles to be orthogonal, this right hand side must be 0. So, therefore, the condition is that two circles S1 and S2 whose equations are given here. So, two circles S1 and S2 are orthogonal if and only if this expression is 0, which basically means that 2 G1 G2 plus 2 F1 F2 equals C1 plus C2. So, let us take a couple of questions to make this concept a little clearer. So, here is the first question. It is said that a circle S passes through the point 0 1 and is orthogonal to these circles, to these two circles. So, let us say that the circle S has this equation, and since it passes through the point 0 1, this equation must be satisfied with x equal to 0 and y equal to 1. And therefore, we get one plus 2f plus c equals 0. Also, this circle S is orthogonal to both these circles. So, since it is orthogonal to this circle, we can use the condition for orthogonality. So, we can use this condition. So, this equation can be written as x square plus y square minus 2x minus 15 is 0, and the second circle is x square plus y square minus 1 is 0. So, so here let us say, so if we consider the equation here to be x square plus y square plus 2 G1 x plus 2 F1 y plus C1 equal to 0, then G1 is minus 1, F1 is 0, C1 is minus 15. Similarly, for this second circle, if we consider this to be x square plus y square plus 2 G2 x plus 2 F2 y plus C2 equal to 0, then clearly G2 and F2 are both zeros and C2 is minus 1. Since this circle is orthogonal to the first circle, we have, since this circle S is orthogonal to this first circle, it must satisfy the equation of orthogonality, which is 2 times G times G1, which is minus 1, plus 2 times F times F1, which is 0, must be equal to C plus C1, which is minus 15. So, this is essentially 2G plus C equals 15. So, this was the first equation, this is the second equation. And similarly, because the circle is also orthogonal to the second circle, we have a similar type of equation, 2g times g2, which is 0, plus 2f times f2, which is also 0, equals c plus c2. This is the third equation. From this third equation, we clearly get c equal to 1. And if we use that information in this first equation, we will get f to be minus 1. Now, since c is equal to 1, if we use the same c equal this information of c equal to 1 in the second equation, we get g equal to 7. So, then we have gotten all the parameters of this circle S, and clearly the center of the circle S is minus g comma minus f, which is minus 7 because g is 7 and minus f will be 1. So, the center is minus 7 comma 1, which means that option C is correct and option D is wrong. And the radius is equal to square root of g square plus f square minus c, will come out to be 7. So, option B is correct and option A is wrong. So, let us consider another problem. So, here it is given that a circle passes through the point A comma B, and this circle, let us say, denoted by S, and it cuts another circle x square plus y square equals k square orthogonally. Then the locus of the center of the circle S is one of these 4 options that we have to find. So, let the equation of the, let us say that the center of circle S B let us let the coordinates of the center of circle S B, let us say P and Q, then the equation of this circle S will be x square plus y square minus 2px minus 2qy plus c equals 0. Now, it is said that the circle S passes through the point A comma B. So, what that means is that this equation should be satisfied with x equal to A and y equal to B. Therefore, A square plus B square minus 2AP minus 2BQ plus C is equal to 0. This is the first equation that we get. And then it is also said that this particular circle S is orthogonal to another circle, let us say S prime, whose equation is x square plus y square minus k square is 0. So, we use the condition of orthogonality, then what we get is, so 2 times g1 times g2. So, the g of the g1 for this first circle is minus p. So, 2 times g1 times g2, but the g2 here is 0, and then plus 2 times f1. So, f1 is minus q times f2 is 0 equals C1 plus C2. So, C1 is C and C2 is minus k square. So, since these two circles are orthogonal, this equation must also be satisfied. So, this equation basically comes from what we had shown in one of the previous slides to be the condition for orthogonality between two circles. So, from this equation it is clear that C must be equal to k square, and therefore, the equation of this circle S. So, therefore, if we use this fact in equation 1, what we get is that the coordinates p and q of the center of the circle S must satisfy the equation a square plus b square minus 2 ap minus 2 bq plus k square equals 0, or in other words, so what this basically means is that the coordinates p and q of the center of the circle S must always satisfy this equation, and therefore, the locus of the center of circle S is a square plus b square. So, let us say that this will be a square plus b square minus 2a times the x coordinate of the center. So, let that be x minus 2b times the y coordinate of the center plus k square is 0. So, the locus of the center is essentially this equation, which is actually a straight line equation because it is linear in both x and y, and this is nothing but the first option, which is option A. So, let us move on to a new topic, which is defining what is known as the radical axis of two given circles. So, suppose that we are given two circles. So, let us say this is circle S1 and then we have another circle over here, let us say S2. Now, consider all those points such that we will only consider those points P such that the length of the tangent from this P to both the circles are equal. So, let us say that these are the two circles with centers O1 and O2, and P is a point such that the length of the tangent PA from this point P to this first circle S1 is equal to length of the tangent from P to this second circle S2. So, we will only consider those points for which PA and PB are equal. In this case, at least in appearance, it does not look like P and PB are equal. So, if they are not equal, then P will not consider P as one of the points in which we are interested. So, the locus, so there is not just one unique point which has the same distance whose length of the tangent to both the circles are equal. There are infinitely many points, and the locus of all these points, as we will see soon, is a straight line which is actually called the radical axis of these two given circles. So, let us see how to derive the equation of this radical axis if we are given the equations of the two given circles. So, suppose that we have two given circles S1 and S2 having centers O1 and O2, then we are always considering those points, which have, for whom the length of the tangent to both these circles are equal. So, for example, if a point P has to lie on the radical axis, then the length of the tangent from P to the first circle, let us say PA, must be exactly equal to the length of the tangent from P to the second circle, PB. So, PB and PA must be equal. So, for this to happen, so let us say that we are given the equation of the two circles to be as follows. So, we are given the equation of the two circles and we have to find the equation of the radical axis. Now, suppose that there is a point P having coordinates x, y. The center of the two circles are of course minus G1 minus F1 and minus G2 minus F2. Now, so this has to be 90 degrees. So, the length PA or the squared length PA square is equal to O1P whole square using the Pythagoras theorem, because this triangle O1AP is a right angle triangle. We have PA square is nothing but O1P whole square minus O1A whole square. And this will, if we do further calculations, as we had already seen in one of the previous lectures, the squared distance of this line segment PA will be equal to x square plus y square plus 2g1x plus 2f1y plus c1, where x and y are actually the coordinates of this point P. So, we have taken x and y to be the coordinate of this point P. In that case, the squared length PA square, and PA square, if you also recollect, is called the power of this point P with respect to the first circle. Similarly, the power of this point P with respect to the second circle will be PB square, which is equal to x square plus y square plus 2g2x plus 2f2y plus c2. Now, now since PA and PB are equal, it follows that the coordinates x and y must be such that this expression and this expression are equal. That is, so this two should be equal. And from here we get that the coordinates x and y of this point P must satisfy the equation 2 into g1 minus g2 into x plus 2 into f1 minus f2 into y plus c1 minus c2 equals 0. So, we see that all such points whose power with respect to both the circles are equal, the coordinates of all such points must satisfy this equation, which is nothing but the equation of a straight line, and this straight line is called the radical axis of these two circles. So, we will get many points like that. So, just like P will get another point probably here, such that this length and this length are equal. Similarly, there could be another point here, such that this length of this part of the tangent to the first circle, and then this length which is part of the tangent to the second circle. So, this and this length will also be equal. So, there will be infinitely many such points, and if we all join all these points, we will get this straight line, whose equation is this, and this straight line is called as the radical axis of these two circles. It is also not very difficult to see that if two circles were to intersect each other, then we have already seen that the equation of the common chord. So, we saw that in the last lecture, or maybe the lecture before that, that the equation of the common chord. So, the common chord is the point, the straight line joining the 2 points of intersection, and we saw that the equation of the common chord is nothing but so this is the case where the two circles are intersecting with each other. So, in one of the previous lectures, we have already seen the equation of the common chord to be this particular equation, but then this is nothing but the equation of the radical axis. Hence, when two circles intersects, the radical axis is nothing but the common chord. We just have to extend it further in both the directions. Another case could be when two circles touch each other at one point, and in that case one can show that the radical axis is nothing but the transverse common tangent between these two circles, whose equation will be, in that case, will be the same as this equation. Also, if we go back to this equation of the radical axis, then it is not very. So, the equation of the radical axis was this equation. So, the slope is the slope of this straight line so, the slope of the radical axis, which is a straight line, is minus of g 1 minus g 2 by f 1 minus f 2, slope of radical axis. The slope of the line joining the centers O1 and O2 of the two circles is F2 minus F1 by G2 minus G1. Now, if we take the product of these two slopes, we see that the product is minus 1. What that basically tells us is that the radical axis is always perpendicular to the line joining the centers of the two circles. Now, given that we know what is meant by the radical axis between any two given circles, we will now define what is known as the radical center of any three given circles. So, suppose we are given three circles like this. So, let us say that the equation of the centers are at O1, O2 and O3, and let us say that the equation of the first circle is S1 equal to 0. So, it is basically the equation of the first circle will be x square plus y square plus 2g1x plus 2f1y plus c1 equals 0. And similarly, we will have similar equations for the other two circles. And for the third circle, so this is G3. So, x square plus y square plus 2g3 x plus 2f3y plus c3 equals 0. So, let us say that these three equations are given to us, and we are asked to, we will basically define what is meant by the radical center of three circles. So, we already know that the equation of the radical axis between the first and the second circle is a straight line. So, this straight line need not pass through the center of the third circle. This is just an example. So, it need not pass through the center of the third circle. So, this is the radical axis between the first and the second circle, whose equation is basically S1 equal to S2 or S1 minus S2 equal to 0. So, from here S1 minus S2 equal to 0 will be, so that equation, so this equation will be simply what we have seen in the previous slide. So, the radical axis between S1 and S2 will have the equation two times G1 minus G2 x plus 2 times F1 minus F2 y plus C1 minus C2 equals 0. And similarly, we will also have a radical axis between S1 and S3, between the first and the third circle. So, let that be shown by this green line here. So, this is the radical axis between the first and the third circle, let us say. And the equation of this radical axis will basically be S1 minus S3 equal to 0, which will be 2 times g1 minus g3 times x plus 2 times f1 minus f3 times y plus c1 minus c3 equals to 0. We will call it C. In the following, what we will show is that the radical axis between the second and the third circle will actually pass through this point of intersection of the radical axis of the two radical axes that we have already seen. It will be something like this. So, what I have drawn in red is the radical axis between the second and the third circle. So, in fact, the three radical axes between the three pairs of circles are, or all three of these are concurrent at one point, which we have denoted by C, and this C is then called the radical center of these three circles. But we need to first show that the radical axis between the second and the third circle will indeed pass through the point of intersection of the first two radical axes in blue and green. The equation of the radical axis between S1 and S2, which we had drawn in the blue line, is similarly the equation of the radical axis between S1 and S3 is and the radical axis, the equation of the radical axis between the second and the third circle is so these are the equations of the three radical axes for the three different pairs of circles. Now, we saw that these two radical axes were intersecting at a point C. Now, from our lectures, from the lectures on straight lines, we already know that the equation. So, suppose if we have two straight lines, L1 equal to 0 and L2 equal to 0. So, these are two straight line equations which intersect at a point C. Then we know that the family of straight lines passing through this point of intersection C is given by the general equation L1 plus lambda times L2 equals 0, where lambda could be any real number. We choose different values of lambda, we will get different straight lines, but then all these straight lines, no matter what value of real value of lambda we choose, all these straight lines of this form will pass through the point of intersection of these two straight lines. So, this we already know. So, applying this to our case, so let us say that this is the first line L 1 equal to 0 and this is the second line L 2 equal to 0 and both of them intersect at this point C, then clearly the equation of the family of straight lines. So, any straight line which passes through this point of intersection C can always be written in this form L 1 plus lambda L 2 equal to 0. So, L 1 is this plus lambda times L 2 is this So, L 1 plus lambda L 2 is 0. So, this for any lambda, any real lambda, this is also the equation of some straight line, but this straight line which we have written here will pass through the point of intersection of the two radical axes, which is this and this, which we have denoted by C. If we take lambda equal to -1, then we get a specific straight line which is given by, whose equation is given by. So, clearly even if we take lambda equal to -1, we get a straight line which will pass through C, and that straight line is 2 times g1 minus g2 into x plus -1 times equals 0, and if we simplify this straight line equation, what we get is 2 into g3 minus g2 into x plus 2 into f3 minus f2 into y plus c3 minus c2 equal to 0. But then this equation, so this equation is the equation of a straight line which passes through that point of intersection C of these two radical axes. So, the point of intersection C of these two radical axes, but then this straight line is nothing but it is same as the third radical axis between the second and the third circle. So, this equation is the same as this equation. So, this is nothing but the radical axis between circles S2 and S3, and we already know that the point of intersection of the first two radical axes lies on this straight line, and therefore, it is clear that the radical axis between the third pair, which is S2 and S3, will also pass through the point of intersection of the first two radical axes. Essentially, what that means is that all these three radical axes are concurrent at one point C, at a point C, and this point is then called the radical center of the three circles. In the next lecture, we will discuss as to how to derive the equation of a family of circles. For example, the equation of all those circles which pass through the intersection of two given circles, or the family or the equation of all circles which pass through the intersection of a given circle and a given straight line. So, we will see this in the next lecture. Thank you.